Let's practice computing the change in specific entropy for air as an ideal gas. So we're given that we have some ideal air in a piston. We're told the initial pressure and the initial temperature, and likewise we're told the final pressure and the final temperature. And so here's our piston. Now, just looking at that, you may not immediately realize whether it's supposed to expand or contract. It may not matter for this problem, but you can remember you can use the ideal gas law to say that P little v equals RT. So it must be the case that the ratio of T over P tells you whether the thing expanded or contracted, and sure enough, in this case, the piston must have contracted. The second volume is smaller than the first. Okay, so the good news is we actually know exactly how to compute the specific entropy change for an ideal gas, and it's using this expression that was in the previous video. The bad news is that we have to figure out what to do with that specific heat integral, because actually, if you look in the back of your book, the specific heat at constant pressure of air does vary quite a bit between 300 K and 500 K. It's a large temperature range, so you can't simply pull Cp out of that integral, which would make the integral a lot easier. So we have to find a way of coping with that, and that's really the point of this exercise. In your lecture notes, a variable is defined. I call it S degree. I've never actually heard its name pronounced out loud, but S degree is an intuitive name for what is written S with a little degree sign above it. So that's a function, and it's defined to be the integral from some reference temperature T prime to a temperature T of Cp dt over T. So it has the general form of the integral we're interested in, but it's from a specific reference temperature, and the value of that reference temperature can be found in your textbook. The nice thing is you don't need to know it in order to use it. Let me show you what I mean. So we're going to pull a calculus trick here, and we're going to separate the integral that we're interested in, the integral from T1 to T2, into two integrals, each of which refers to the reference temperature. So the integral from T1 to T2 of that quantity, you can split into the integral from T1 to T prime, plus the integral from T prime to T2. That is equivalent to the left-hand side, which is the integral that we actually have in our formula. Well, we can reverse the first term on the right just by reversing the limits of integration and putting a minus sign out front. So now we have two integrals on the right-hand side that are from T prime to some temperature. Now the two temperatures are different. The upper limit of integration is T1 in one case and T2 in the other, but in both cases we're integrating now from T prime, some reference temperature, to the temperature that we're actually interested in. Well, that's nice because we just defined this variable, S degree, that is exactly those integrals. So we can rewrite those in terms of S degree, and what we would say is that the integral we're interested, integral from T1 to T2 of Cp dt over T, must equal negative now S degree evaluated at temperature 1 plus positive S degree evaluated at temperature T2. We can rearrange this just because nobody likes minus signs out front into being the integral we're interested in is S degree at T2 minus S degree at T1. And you may say, okay, I just parameterized this in a really weird way, but we don't know the values of S degree, so why does that even matter? The answer is that we do know the values of S degree. We know because your textbook already computed them. So if you turn to table A22 in the back of your book, you'll see for ideal gas air that indeed there are values of S degree listed right next to the temperatures that you need, so we can use that and look up S degree at 300 Kelvin. That's S degree at T1 is 1.702 kilojoules per kilogram Kelvin. Likewise, we look up the value at 500 K and find that. Now the problem is that these values are only listed for air, and of course only for an ideal gas, and they aren't listed on the NIST website. So right now, if you encounter a problem like this using ideal gas air, the only way that we currently know how to do it, if the specific heat varies over temperature, is to use table A22 in the back of your book. There's currently no other way that we could get at this. Okay, so let's do that for this problem. So we write out the full expression for the change in specific entropy, and that's that S2 minus S1 must equal that integral that we now have a form for minus R ln of P2 over P1. Well, we can plug in all of the stuff now, so we can substitute for that integral the difference between S degree evaluated at T2 and evaluated at T1, and now we can just plug in all these numbers. So we looked up the two values of S degree. We can figure out the value of R from knowing that the molecular weight of air is 28.97 kilograms per kilomole. We take the ln of 4 bars over 1 bar, simplify this a little bit, and finally get a change in specific entropy, S2 minus S1, of 0.1197 kilojoules per kilogram Kelvin. So that's our answer. If you didn't know the values of S degree in this problem, you would actually have to explicitly model the behavior of Cp as a function of temperature. Now maybe it's simple, maybe it's just linear or something like that, but it would still be a big pain. We'll talk about alternatives to this approach eventually in this course, but for now, if you get ideal gas air and the specific heat is not constant, you better use table A22 and the values of S degree.